Thank you for coming to my talk. This talk, you all know because it's on the architecture track, but it's on the between soft skills and hard technical proofs and stuff. This talk is pretty deep into the technical practices with a little bit of code. So if that's not your cup of tea, this is your chance to find something you like better. Also, I should mention there are a few hidden gang of four patterns in the talk, and it could be fun for some of you to see if you can spot them. All right, let's jump into it. My name is Christian. I started out as a consultant, then transitioned to tech leadership, and then now I call myself founder. I wrote a book, which I'm very proud of. Does any of you own the book? One person, one person. Cool. Well, then a lot of new customers I see. Great. Cool. All you need to know about me to follow the talk is that I'm obsessed with code quality, and particularly resilience, or reliability, sorry. My life is too short for buggy code and freezes and crashes and all that. And also speed. I don't think humans should wait for metal ever. Like, software should just respond and be fast. And I also want to come with a quick disclaimer before I get too deep into this. This story is told like one story, but it's stitched together from different projects. It's not one project that went from nothing to everything. And all of the examples are anonymized due to NDAs, and I don't want to overwhelm you with boring context. As my mentor used to say, I point to the moon, don't look at the finger, right? The examples are not the important part, the ideas are. All right, cool. So this story starts with a big project, million lines of code as usual, that was developed over many years by a bunch of different teams. And it was all deployed as one unit, so a standard monolith with no quality assurance whatsoever. So very standard starting point for a refactoring type story. And I was put on this project because there was a problem with the address component right here. It gave an error. And I really want to improve this architecture. I consider myself a software architect also and a refactoring guy, but I'm also super busy right now, so I guess I'll just go in and fix it quickly. It's a small problem, and then we can just, I implement a quick fix, and then I start deploying it. And the reason I say start deploying it is because it was a bit of a process on this project. We had to first build the code, then zip the bin folder, then we had to upload the artifact to Dropbox, then we had to log into a jump host, then we had to log into the server, then we had to extract pull the artifact, sorry, and then we had to extract it, restart the IIS, and then hope that it all worked. And this whole process took about 30 minutes. And then, of course, you extracted it in the wrong place, so you had to go through most of it again. You can do another 30 minutes, and you compiled it in debug mode instead of release mode. It's a C# project. Okay, 30 more minutes. This is heavy, right? And it sucks. It's very boring work. I actually did deploying it right after a while, and said to the customer, it's working. And instead of thank you, they said, it's not quite working in production. Did you deploy it? And I'm like, I deployed it a lot, actually. So that's not the problem. It turns out there were different address components scattered around this code base. And not only that, they were broken in different ways. The top one here doesn't extract a number from specific types of addresses, and the bottom one doesn't extract the street from other addresses. So like all three were broken. So I was like, okay, fine. We have some problems with this code base, right? Let's take stock. Deployment is error prone. So first step, quick, just script it, put it in a CI system. That's hopefully not a revolution to say today. Back then it was pretty cool. We have two other problems though. The code quality is poor and deployment is slow, and they're gonna take a little bit more work to fix. So let's start the journey. Raise the code quality. First step, I like to start by just killing a lot of the old stuff when I do something like this. So I deleted all the stupid duplicate implementations of address things and implemented a correct one. And I did it right? I did it all the right tricks. I had test, integration test, unit test, the whole thing, right? Really good. I felt like I was doing my part to improve this code base. 2 days later, my component breaks. And I'm like, I wrote all the tests and stuff. What do you mean that it broke? So I went in and checked, and it turned out that we were using a third-party service, and without telling us, they just changed the interface to that, right? It just sent back a different format, and it was like, yeah. So we had to insulate our code, or isolate our code from their code. Enter, of course, you know it, the layered architecture. And it looks beautiful, right? The thing is, you only talk to things that are right next to you, and then you can totally isolate all of the changes, right? In theory. The thing is, and you can even see this on this beautiful cake, the blue is sort of reaching into the sort of darker blue, I guess, and also a little bit into the green. And, you know, often in practice, you end up just needing to reach one level deeper, right? Just beyond one of the levels a little bit. And when that starts to happen, it degrades very quickly. And this is more my experience with layered architectures I've seen in production. So I had to come up with a different model. I came up with something I call the spaceship model. And it's a simplified model from the layered architecture or the onion architecture, where our code lives inside a spaceship, right? Where it's safe, it can breathe, all of those nice things. Out here is space. And in space, no one can hear you scream or develop software. It's dangerous. All the danger lives out there. So that's where third-party services, databases, and even the standard library lives. Anything that our team doesn't control lives out in space. And that means for us to interact with it in a safe way, it needs to go through an airlock to get into our code, right? Where we then deal with all of the changes and all of the whatever people do with these things. And it looks nice on a figure. Let's look at how it, let's see how it looks in code, because it's actually very simple to implement. I do two things. First of all, I put a namespace at the top, so I know that this is intended to be an airlock, and the code in here isn't pristine code, because that's not its job, right? It's not the job of this to be good code. I don't care. The only thing it has to do is map from their data types to data types that I control the interface of, so that I can move code back and forth and be really flexible in my inner core, in my spaceship, right? So everything that's in my spaceship, I put there and I control. And I'm not saying that you need to re-implement linked lists and arrays and all of that from the standard library. What I am saying is you should wrap it in classes that you control, so you can monitor the interface, and so that if it happens to change, you can isolate that change to the airlock and not to your code. So changes have a limited scope. They can't just run rampant through the code base. And also, and this is a secret that not everybody knows, classes are free. Right? You can create as many of them as you want. And when I realized that, I was like, I create so many classes now. Like, consider this example. We have a login thing. It takes a string, a password, and a username. And here we have two calls to it. And apparently we've forgotten sort of which way these strings are supposed to go. Very easy mistake to make in a system like that. But if we just completely trivially wrap those strings in a username and password class and then type these, we can now, the compiler, the type system will tell us the bottom one doesn't work, right? It tells us forever. All the times we call this, also in the future. Even if I go and swap the order of these at a later point, it will tell me everywhere I need to go and change that. So this is a really great help. Okay, let's get back to the code base we were working with. So we've improved the code quality by just rewriting the code, and we've isolated the third-party danger by using the spaceship architecture. Deployment is still slow, and it's slow because we're carrying around an entire monolith every time we want to do anything. We have to build everything and deploy everything. So I want to separate my new component, the address component, out into its own compilation unit that I can deploy separately optimally. The problem is that in my rewriting of it, I've discovered that it's actually dependent on something in the rest of the code base. And so when I try to pull it out, it's like, should I compile this first or this first? Because they depend on each other. We can't compile them at the same time, apparently. So that was a bit of a problem. So it's this one. And there are three ways that we can deal with a circular dependency like that. The first one is we can use higher-order functions. And yeah, so that looks like we have sort of a shipping component up here, and then we have an address component, and then the address component uses shipping, and the shipping uses the address. So instead of that, we can take this call to shipping, and then we can extract that into like a high order function here and just send it up here. So now shipping depends on itself, and address doesn't depend on anything, technically. So we could pull it out and compile it separately. This works very well if you still want to deploy a monolith where all of the code gets eventually bunched together anyway, or library, something like that. But I intend to pull it out so I can deploy it separately, and then this is not the best choice. Second choice is to use REST or something similar, remote procedure calls, direct communication microservices, as it's called. And that's very easy to illustrate. You just delete the blue line, and where these lines were method calls before, they are now just REST calls, and it's the exact same drawing. The problem I have with this is that an architecture like this, a communication architecture, needs to be flexible. It needs to evolve with the code. As we learn more, we add more responsibilities to the code, and it needs to move, right? It's a living, growing thing, and it needs to be able to accommodate that. And when we have these arrows and things, if we want to say one of these components grows too large, right? Code always grows. We only add to it, it seems. So component B, let's say, is too large, and we want to split it into two. So the first thing, we can do this with sort of a strangler pattern thing where we already have component B, so we'll just forward the calls through B out to the new services, right? That's fine. Our team can do that. The green team can do that with no problem. And all the other arrows are the same. The thing is now, we have this empty shell that just forwards to two other things, a load balancer of sorts, or whatever you want to call that. But now, in order to get rid of it, we actually need the blue team to go in and change this arrow in their code base, and we need the yellow team to go in and change this arrow. And I don't know if you've tried to get tickets into another team's backlog. It's really, really hard in practice. So what ends up happening is we can't get rid of this stupid empty shell that doesn't add any value. It's just extra complexity in our infrastructure that just sticks around forever. And I like to say that it's like sand in a machine like this, right? Over time, it gets very hard to move in it. Okay, so I don't really like direct microservices. So the third option is to go event-driven. Or indirect microservices. And if we just look at how that deals with this small circular dependency we had and do it step by step, the first thing is to introduce facades in front of the components we have so they don't call each other directly. And that looks like this. So now address calls the facade, and then the other one calls the facade as well. So that's a fairly easy change to make. The next step is to introduce a queue where these meet in the middle. Right? So that instead of them talking to each other, now they actually just post something to the queue, and then the facades become observers that then listen to the queue for a thing that's relevant for them. Right? So now we don't have the circular dependency anymore. In fact, I've also colored them in different colors because we can very easily split these into separate compilation units. A queue actually doesn't need to know anything about either of those, so we can compile it separately or use a standard one. And the other two can then be compiled together, or the yellow with the yellow and the gray with the gray. The third step is we can take an observer. Really is just a very small queue, right? That takes one thing and passes it to another thing. What if it could just take multiple things, right, and then pass those in turn? So then it becomes like this, and I've used RabbitMQ vernacular here, so they call the middle one an exchange, and then the other ones are queues, but it's the same sort of idea. We have a big queue distributes to smaller queues that then send it to their specific things, which is really cool because now we can compile everything separately, and the only thing that has to be redeployed is the thing that we actually changed, right, in the component or in the address service. So I said before that you could also do sort of the split and stuff with the REST. So let's see how this code or how this sort of system will handle a refactoring like the one we did before. So we have the B component and we want to split it up. And I call this the blackjack refactoring pattern. Let's see if you can figure out why. The first step is to split the service inside of the one service. So you split all the code, so it's still in the same service, but they're disjointed. And that also means that we hook it up to a different sub-queue, sort of like this. So now the queue is split up, but the service is still the same, and it just subscribes or observes on both these queues. The next step is to then duplicate the B service entirely as it is, like no change at all. We just copy and paste a different code base, so we have two identical, and that means they'll both listen on all of the same services, or all of the same messages from both of the queues. So they're still both green. The last step is to go in and remove one of the subscriptions from the queues from each. So B1 will listen only to Q1 and B2 will listen only to Q2. And now we can go in and actually delete all of the dead code that's in B1 and B2 without affecting the system, right? With this, you can deploy after each of these steps, and you'll have zero downtime, and you'll have split up a service with your head under your arm, right? You don't need to think about this at all. You can do this on Monday morning, right? It's amazing. Something that's really hard to do in a lot of other architectures. So yeah, split, double, bust, and then you can take something and split it in two. And your architecture is flexible, right? It can move now. It's not as static as it was before, and we have no sanding in the architecture. So yeah, we've split up the monolith, or started to split up the monolith. Let's just fast forward a little bit in time. Say we split up the monolith, and we use indirect communication to address the refactoring as difficult in a direct microservice setup. But now, especially because we're using message queues that are probably standard and not like implemented on our own, we're actually we're limited on our throughput, not in the queues, but in the services, right? They move very slowly. So let's look at how we deal with that. At the time, we were working with this sort of stack. We had hardware running an operating system with a container, with the communication architecture, that's the message queues. And then we have packages and dependencies in our code, and then we have our code. And all of this requires maintenance, right? All of this can have flaws, and all of this can have zero-day attacks and all these other things. So we need to go and patch it, and it all takes time, and it takes expertise, and it's super hard to maintain. So at the time, we were considering whether to move to virtual machine setup, where we don't have to at least maintain the hardware, or go to this new thing that was just out called Serverless, where we also didn't have to worry about the operating system. We'd still have to probably ship a container and still have to do all the other things. So we were considering this choice. Since I had to make this decision, the field has moved forward, and I'll just, for your sake, show you what it looks like today, because there are a few more. Now we also have front-end first or back-end as a service providers, where you just ship your code and they make the container, and you still have to figure out how you want them to communicate yourself. Or you can move even a step further, where the communication architecture is provided as a service, so you don't have to deal with it and set it up and worry about availability and stuff. And you can even started to come out something called semantic patching that will update your dependencies and update your code to match it, so you don't have to spend time doing that. So yeah, we're moving this upwards in the hierarchy. So back to our decision. We were wondering, virtual machines are serverless, and on our list of important points, we had a really cheap runtime for virtual machines. They're really cheap to run. On the other side, we had easier scaling with serverless. We have less waste because they are turned off when they're not doing something. We also had less maintenance, and we were billing 200 to 300 euros an hour. So it actually adds up very quickly compared to the runtime, which adds up comparatively slow. We could deal with a lot of extra runtime for the time we would save on maintaining the code. And so we started working with serverless, and we came across another problem that we hadn't thought about, and it was cold starts. Cold starts are one of those things that's really hard to get a sense of until you run into it in practice. It feels like, yeah, but does it really matter that much, right? I already told you I'm obsessed with speed, but so are the giants. And it's for a good reason, right? Amazon made a test where they found out that every 100 milliseconds of latency, that's less than we can humanly feel, right, cost them 1% of profit. So, like, this is on the this costs money. And Google did a similar thing where they found out that if they added half a second, they dropped 20% of their traffic. So it kills user satisfaction. Speed is really important for software that touches, either delivers to end users or that other software depends on to deliver quickly. And the seconds add up if we have cold start. So the three clouds we were considering at the time, right, the three big ones, I just want to give you a sense of what their worst case cold start is, just so you know what I'm talking about, right? And I'm just going to stand here quietly while you experience the cold start. Cool. Did you feel it? It's like, and these can cascade, right? These can come one after the other. If you have other services calling other services, you can end up waiting a long time for some of these things. So there are three solutions to deal with this thing. So the first one is just pay to keep them hot, which is the simplest solution, but it again eats into the fact that people already consider serverless to be fairly expensive. We can also set up cron jobs to fake that it's hot, right? We set up more infrastructure to deal with the lack of our current infrastructure. And that also, in my opinion, is like sand to software development, right? Because we're just adding more stuff we have to carry around. And when you split up a service now, you have to remember to set up an extra cron job to keep both parts of it hot. And yeah. You could also, and this is more of a modern solution, look for platforms that actually have at least non-cascading cold starts or just no cold starts at all, would solve this sort of problem. We had to come up with our own way of avoiding cold starts. And we actually solved all of our problems on our list by using serverless and doing it without cold starts. But some funny things have started happening with our software, because we started out with a fundamental property that was, we had a sense of time in our program. And now that we've cut it up in all of these ways and distributed it on these different computation units, we have swapped that out for a sense of progress. And that's a weaker fundamental assumption, right? And that means that we now got race conditions and deadlocks. We got lost messages, repeated messages, congestion, memory leaks, and cascading failure. Fun stuff. This is when I started losing my hair, and also when I started calling myself a senior. These are not easy to deal with. The way we tried was to run faster, right? We tried to control it tightly. We tried implementing consensus and leader election algorithms, right? To make sure everything was coordinated. We also tried putting locks everywhere to avoid all of the race conditions and things. In essence, we tried to control the chaos. And all of that turned out to be misguided, fundamentally. The strength and power of a distributed system comes from the chaos. And so the solution is to embrace the chaos and to work with it instead. So it was time to crawl up on the shoulders of some giants. So the first step was to make all of the services stateless. And as Netflix does, start killing things randomly. And at first, I'd heard about this killing things randomly, and I sort of knew, well, the thing is, it forces you to do statelessness, right? Because if it isn't stateless, then you're going to have a problem when you start killing it. And I'm like, okay, that's fine. But after I started doing it, I realized there is a much deeper impact to doing that I don't feel like people talk about enough. So first of all, it forces graceful shutdown. If your services take down file handles or database connections with them, you're going to run into a problem when you start killing them, right? Because those are just not coming back until the things flush their cache or does whatever it does. So you're now starting to do graceful shutdown, which got rid of most of our memory leaks. It also encourages fast startup times. So your services, if they get killed often, have to come back online quickly. So that's immediately helpful when you actually have an outage or something like that, and you need to swap something out or try something out, do some different things, change the configuration, do all of this stuff. Having fast startup is really cool. But finally, and I think the biggest effect of killing things in production is it forces seamless failover. Because if you don't have a seamless failover, you'll have an outage every time you do this. And obviously, as the DevOps saying goes, if it hurts, do it more, because then you'll fix something like this and you'll have 2 copies running, and if you kill one of them, it'll just switch to the other one seamlessly. And this is really, really helpful if you don't like getting up at them in the middle of the night and you're running some critical software. Once you start doing this, it's going to feel like crossing a frozen river, right? Really uncomfortable. But I promise you, there is pizza on the other side of the metaphor. So it's totally worth it, in my opinion. And we do it as much as we can with our software now. We kill everything we can think of. So a little bit of progress. We got rid of the memory leaks and the cascading failures because now things come back up, and they come back up quickly. We still have lost and repeated messages. And looking back, we have this stateless property in our software now. That means that running something before a shutdown has the same effect as running it after a shutdown. But we decided to swap that out for a stronger property called idempotency, where running something once is the same as running it twice or any number of times, right, by induction. And in code, that looks like we have some SQL over here. It has an update in a visit table and then a counter that increments. We can't call that more than once, right? If we call it multiple times, it's going to increment the counter too many times, and it's not going to be accurate anymore. So we swap that out with some code that instead inserts a unique identifier. And if that identifier is already in the database, it just does nothing, right? And this we can call as many times as we want. It will only affect the state once. Only the first time we called it. It, of course, also means that every event has to now get a unique identifier that we can use to say we handled this event in this table or in this thing. And yeah, the select changes a little bit, but it's fine. So that means if we look back at our properties, we had the repeated messages. Well, with idempotent services, it's literally not a problem. That's the thing we've built into the thing. And lost messages, though, we can just repeat, right? We can just send them in multiple times, and every time they fail, just send them in again. And if we don't know whether they failed, send them in again, because repeated messages is no problem. So that works really well. In essence, what happened with all of our, we had this nice database CRUD sort of set up before, and what happened when we started doing this was we got rid of all of the updates. Really, is to say it briefly, essentially making all of our data immutable. And that's because idempotent services go really well with immutable data. And that's really nice because most of our locks were when we were updating data, right? That's when we can get race conditions and stuff like that. So because we're no longer updating data, we don't have those race conditions and deadlocks anymore. So, and we also don't have lost and repeated messages. So we're getting really close. We still had congestion in the system. And in fact, congestion got a little bit worse because these operations, especially delete, is a little bit slower than updating things in the database. And so if delete is slow, there's a fairly simple solution. Don't do it. And so instead of having calls that were like, delete everything from before today or whatever we did before, this can take hours or days to run, right? Because it has to go in and examine everything. It takes forever. Instead, we switched to using petitions where we would just drop an entire petition at a time. And that's really fast, like milliseconds. It takes no time at all. It's a little bit of setup to get started with this because you have to set up some services to renew your petitions or make sure you don't run out of them. A little bit of stuff like that for the first one, but then it's trivial to reuse for the rest of the stuff afterwards. And you might say, well, in a visitor counter table, I would preferably want to keep sort of the tally, right, of how many we've actually had. It's annoying if every 2 months we reset the counter. So to solve that, we instead of just dropping it, we added a weight column or an attribute to the table. And right before we delete a petition, we go in and then we insert a new entry with the sum of all of the weights we're deleting, so we can carry it forward. So 99% of the entries just has weight 1, and then there's one at the end that has weight whatever has been deleted so far. And so that works really well also. And we got rid of our congestion with petitioned and truncatable data, if that's even a word. Cool. As a last thing, I just want to share with you how we ensure that the quality stays high in our code bases. And so the first category of things we use is mastery, and it's like watchmakers can make more precise watches if they're better at their craft, right? I don't know about watchmaking actually, so I should be careful. We practiced it by reading and by practicing and by experimenting a lot. You know, if there's something we don't know, we like to reserve time and try to go in and just do something crazy and see if it works, right? Because we don't know. Programming is fundamentally unpredictable, and so the only way you can gain any knowledge is by trying it out, really. Yeah, and especially if you're sort of at the edge of your knowledge or the team's knowledge or even humans' collective knowledge. We also have some tool assistance. You can see in woodworking, it can actually make quite a significant difference, I would argue also in software. We rely very heavily on strongly typed languages and the type system in general, and that's just a thing that I've done since university. I'm a type theorist, I love it. I love trying to teach the type system everything I can. We also have like a local simulator. We can spin up everything from the production system on a local machine or any subset, and then we can see how it will behave if we simulate one of these flows because it's event-driven, right? That also means we don't have a test system because anything we could find on a test system, we can find on our local machines, and the rest of things can only be found in production. Emergent behaviors and things, there are just some things that only production can show you. Yeah. So we only use our local simulator. We also have the slow rollout on everything. So when we deploy something, it'll take about an hour until it hits all of the nodes or all of the users or whatever. And that means that if we deploy something that somehow is a bad deploy, we can usually stop it before it's rolled out and start reverting very quickly. And we'll get very fast feedback from production using this. Yeah. Completely analogously to how we do with our deployments that are generally scripted now, we also have a scripted diagnosis that pulls all the different parts of the system and just reports back which ones said yes and how fast and stuff like that. And it's very uncommon. I don't know why. It's really smart. Then we have testing. And it's like a chef tasting the food to make sure it's seasoned just right. We use that in different variations. We have smoke tests on everything. Nothing can go in production if it can't start, right? It doesn't get routed traffic to and stuff like that. That actually catches most of our problems. It's amazingly powerful. Just try it out in the production environment. If it doesn't run, it doesn't have a database connection, if there's something wrong with something, just don't deploy it. We also have some unit tests. They're mostly in the parts of the code that rely on untyped languages like Go or something like that. There we use unit types to compensate for the fact that we can't use types. And we have system tests. So we have a third-party system constantly polling our system to make sure, or sending in a request that goes through all of the parts and then returns to make sure it's always online and working. So this is really also a safety thing, right? I know I don't have to test it right now. I know it'll pass because somebody else just tested it less than a minute ago, constantly. Cool. We have fault tolerance, and it's like these roller coasters actually, if they lose power, people don't die. Whoa, that's crazy. They stop in sort of a safe thing, right? They have all of these, I think it's called default closed. And likewise, we can build into our software that we replay failed events, right? We can build in these things that default take care of things. As I said, we have seamless failover, so that means we have nothing that only runs one copy. Everything runs at least two. The more critical it is, the more copies we run, so it's harder to take it down, and also can handle scale better and stuff like that. So yeah, a resilient thing. We also have some code that tries to detect and avoid bad nodes, but it's a little more specific to our situation. But it also it speaks to the fact of building in fault tolerance so that we expect things to go wrong and the system can handle it. Finally, formal verification. Airplanes are actually formally verified with something using abstract interpretation before software is put on them. And I hope the same would happen for self-driving cars. They went another way. And we don't generally do a lot of formal verification. It takes a long time to actually sit down and do mathematical proofs. But because we're using independent services and because we're using immutable data, it is much easier to reason about it in a formal manner, to say, oh, I know these properties will be true in the system because I've isolated all of these invariants, and the components don't generally affect each other. Yeah, so that makes it really easy. Cool, so to wrap up, it's been a long and brutal journey. We're up to where I am in my understanding of how to build software and complex software systems. And one of the conclusions I draw is that some of these problems I've discussed here can be solved once and for all, right? They don't have to be solved every time by a platform. That's the point of platforms, right? We can take some of these things and move them out. That's things like maintaining high availability message queues. It's not something everybody needs to know, really. Optimally, very few people need to know this. Having pipelines in the right way to set up and tear down all of these things, avoiding dead letter queues, all that stuff, and eliminating cold starts. Right? These are things that a platform can handle. And indeed, that's actually the platform I've built. We call it Make, and you can go and try it out. I had to mention it. Other things have to be in the hands of the developers. It has to be something that everybody does with their software. It's something like isolating changes with something like the spaceship architecture. It's something like having at least an equivalent to the blackjack algorithm, if not this directly, to make your architecture flexible and to make sure you can split up things not only within a service, but also across a macro architecture. And it's using 3 I's when we're doing service design. It should be indirect, it should be idempotent, and they should be immutable. And then we get scaling and resilience and a lot of other things just for free, which is really nice. I want to thank you all for listening. Normally I would take questions right now, but I don't think we have a lot of time. So just mention, you can reach out to me. I'm on a lot of platforms. I'm always the same handle. So you can go there. I'll also say, again, because we don't have really time for questions, probably, feel free if you want to talk about code quality, platform engineering, infrastructure, book a meeting with me. You can just do it online. And also, I have a book signing stand thing. I'm over at the book signing stand from 3 to 4. And you can get, I have 5 books to give away. And you can get it if you can name 4 of the hidden Gang of 4 patterns from the talk, or if you bring someone who have read it. Cool. Thank you.